Ekaterina Shemyakova from SUNY, and the title is Differential Operators of the Superline, Berezinians, and Darboux transformations.
Hello again. I'd like to thank very much the organizers for organizing this wonderful conference, and to all the participants who is making this conference very interesting. So here is my contribution to the conference. So I would like to speak about some problem which is somehow related remotely to factorization of linear partial differential operators, something you all understand. And well, in solitone theory, there is a somehow related problem, completely about Darboux transformation. There's a certain notion Darboux transformation. So, and there's a number of results, classification results about these Darboux transformations in the solitone theory. So, but in this talk, this is a couple of steps in my new project. I'm considering all of this in a supersetting, and so yeah. So this is what I'm going to talk about, and I'm trying to find analogous of the classical result in this supersetting. So I'm going to define everything, of course. This is just update, just a heads up. So this is a joint work with my students, Sean Hill and Simon Lee, and with Ted Border from Manchester, UK. Okay, so first of all, I want to say tell you what you're going to hear, so a little bit in yet more detail. So I'm going to, so the result is the following. So for the Darboux transformations of the Superline, we have now complete classification, and we also know how to describe the Darboux transformations. And the formulas are analogous to the classical formulas, but we're going to explain. So the classical formulas are given in terms of determinants, and here we're going to use them in terms of Berezinians, which is super analogous of determinants. So also on the way, we have to work, like if we have to work on some problem in sort of superlinear algebra, you can say, and we found the formula for cofactor expansion for superdeterminants. And also just a little bit on the, I guess we had to further a little bit serial partial differential operators on the superline and discover that they have some intriguing properties. This is what I'm. Okay, so how we're going to proceed, the plan is as follows. I'm planning that first tell you about Darboux transformations, like define them, then about partial differential operators on the superline, explain what's interesting about them, then define Berezinian and tell about this new formula for cofactor expansion, and finally the main results, so this Darboux transformation of the superline, so all of this is applied. So first of all, what is Darboux transformation? So Darboux transformation, it's a mapping which takes ordinary partial linear differential operator to another one, in which they should be the starting operator and the resulting operator should be of the same form. What is of the same form? It's a bit depends from case to case, but you can think about this as for a start, the principal symbols of this operator are the same. That could be more involved. So and also together with this mapping happens the mapping. It's implied also mapping on the kernels of operators and or on the eigenspaces of corresponding to these operators. So this all happens. You can define it easily by algebraically saying that L and L1 they sort of intertwine using some auxiliary operator M, or sometimes you use two operators N and M. So N and M is operators on the same time. So relations with single M was considered in many different papers. So for example, I could mention here the works of Shabbat, Shabbat, Badrov Samsonov, and Beres Silovs. And with possibly different M and N, which you really needed when you consider partial differential operators, this was done in my work with Sergei Tsarov. So now a brief history of Darboux transformations. So the first appear is the study of differential equations and in geometry of surfaces and in works of classics. Euler, Laplace, Darboux, Motat, Seika. And until in 20th century, until 1970s, they were almost forgotten, and so only maybe they were used in quantum mechanics, where actually was essentially this old result of geometries was rediscovered. So this was until the rise of the soliton theory, when Darboux transformations again started to be like a hot topic, and in particular, they were used for constructing solutions for nonlinear differential equations. So here I would a lot of different works, but I'd probably mention only one name, the name of Matveyev, who was responsible for the name of Darboux transformation, so he introduced it, and also he has contributed a lot to the development of the theory of Darboux transformations. Now about Darboux transformations in the superset. So it started in '95 and was done. Pioneers here was Tin-Pin Liu, and later on he worked with Manias. So he considered so-called Supersturm-Liouville operator. So I'm going to, so at the moment just take it as is, so t squared plus alpha d plus u, and I'm going to define what does it mean later. And so they studied Darboux transformation, introduced outside Darboux transformations based on the seed solutions for the separator. So later on they found some Berezinian transformation for the separator and worked in terms of super Bransons. And also there were another team who was working on this with Lee and Nemo. So and they introduced Darboux transformations for twisted derivations, and also work having a formula in terms of composition in terms of quasi-determinants for this Supersturm-Liouville operator. Okay, so now let me speak about a little bit about partial differential operators in the superset. So so this particular work, so the supersetting, this will be so here I was have to probably apologize for a second because there's experts in the audience, of course, but I just have to introduce it for the sake of everybody. I'm going in this particular work, I say it's supersetting, but in this particular, it's a big project, but in this particular result is about the superline. So superline is a one-dimensional supermanifold. So basically, where we basically have one even coordinate and one odd coordinate. So what happens is even with even commutes as usual, so even with odd commutes as usual, and odd with odd commutes with a sign, so you get a sign. Functions on the superline are defined as follows. So here one important just expression of psi. Psi is odd, so psi squared equals to 0. So here one important thing which you may notice that that f naught x in the second line, f naught x can be odd, without dependency of psi. So we would like to be able to do this. So we say that we allow dependence on some extra odd parameters, which we don't specify. Okay, so while we're going to show that we discovered some curious features of the partial differential operators on the superline. So let's get started. But for this, we will need to introduce this operator d capital, which is d psi plus psi dx. So psi is odd, and so one can compute that if you compute d squared, you can just get dx. So d is it's not new. It's well known. It's a operator which is well known to physicists and often appear in the literature under the name of superderivative or variant derivative. So of course, so now let's talk about this ring of partial differential operators. So it's a ring in terms of in two derivations, basic derivations, d psi and dx. So it's partial differential operators therefore. So, and of course, we can introduce a natural and straightforward idea of the order we have on this. However, for our purposes, it's better, and it turns out much convenient to introduce the order in different way. So we say, okay, so we observed, one can easily see that dx and dxi could be both expressed in terms of d capital. Therefore, for any linear partial differential operators on the superline, each of these operators can be expressed in terms of d capital. So we say it's with its normalized form, and we say that the order of the operator is going to be, the order in this, in the degree in this normalized form.
What about d by dxi?
What's it?
What about dxi characterized based on tension and
Just because just because so d right is dxi plus psi dx,
okay.
right, and sorry, this is d squared, so I think it's yeah. So here, just to have a feeling about this, so this is examples. Of course, the order of operator d going to be 1, d capital going to be 1. Order of dx now going to be, the set is going to be 2. Order of dxi also 2. And say, order of the operator which we mentioned before, is super will operator, which was considered, is now order 4. So, what we suggest to consider now is so this is something we figured out to consider. This was to consider among all the operators, such operators consider those which has invertible leading coefficient. So that doesn't look from the first point of view such as significant restrictions that we can classically call them like non-degenerate operators. However, it turns out to be a drastical importance. So first of all, what is non-degenerate operator? The easy example is dx. dx is non-degenerate, and dxi. This is the easiest example of degenerate operator because this representation and the leading coefficient, so it's negative psi, so it's degenerate. So psi non-degenerate. So so now we're going to talk about these non-degenerate operators. So one comment. A little remark. So of course this this ring of operators on the superline, in dxi dx was considered before by Manin, for example, of particular works of Manin and Radu, and but they was like doing slightly different approach. They're doing considering adjoining the formal inverse and d capital -1. Which is basically the same as adjoining D inverse, and they get the ring of formal two differential operators, and our non-degenerate operators are actually exactly the invertible elements in their ring. So now what I'm going to show you is that this non-degenerate operators, they actually having a very nice properties. So first of all, it is possible that you have every operator, some operator n, which is this partial differential operator on the superline, you can always divide it by non-degenerate n, with the remainder both on the left and on the right. Secondly, which is I think very interesting, is that non-degenerate differential operators, they have finite dimensional solution space. So if operator, and more precisely, we know the dimension. So if the operator for the m, where m is odd, so you have n plus 1 more even, the independent solution, and n is odd. So the dimension is showing this way. So here's how many even, how many odd. So and if you have the order of operator even, so you have equal number.
So that is determining what space. You probably should extend space to make it kind of differential.
Yeah.
As a schema.
Yeah. Yeah. So some examples. Yeah. So if you take, say, non-degenerate operator T capital, which I showed before, so if you're solving d phi equals to 0, then you could, small computation, you could show that phi is a constant. So dimension is 1, 0. That's this one. So if you consider like dx, or I just skip this subscript, so if you solve d phi equals to 0, then it's easy to see that phi can be any function of psi, such that phi is c1 plus psi c2, where c1 and c2 have to be constants. So we have dimension 1, 1. And what's wrong with degenerates? So if you take degenerate operator, which is psi, which I showed you before, then, well, phi can be any function of x, so you have a three-dimensional space. So this is what's wrong with degenerate operators. So another thing which I would need, so as you know, the same way as an ordinary differential situation. Every first order differential operator, it's can be represented in this way. Just instead of in ordinary case, just instead of d capital, it's just a usual d. And here it's going to be the same, but we have this d capital, and so the kernel of such operator, which we're going to be using next. So please remember it, and phi is going to be spanned by this phi. So they all look like this. So it's the same as in ordinary case. Also, we have like a Bezout theorem. So if you know one element of the kernel of the operator, one even element, you can divide out. You can construct the corresponding first order operator and kind of divide out. So the left factor L prime is going to be non-degenerate and of order less by 1. By induction, you could also, factorize if you have operator for the m. You can factorize it. You can factorize it in this manner. Okay, so conclusion so far, I think you've seen a lot. So again, I would stress that although we technically have partial differential operators in dx and dx, we essentially have their behavior, if we make this restriction of non-degenerate, we essentially have ordinary differential operators in d capital. Not ordinary, but the behavior, remind us about ordinary differential operators. So we're going to concentrate on Darboux transformation for non-degenerate operators. So now, again, for these Darboux transformations, I need the following facts. I want to show that non-degenerate operators are defined by their solution spaces, and here we have to speak about Wronski determinants. Well, they are super analogs. Of course, they have to be super determinants, which is Berezinians, but they have to be in a special form. And again, I apologize in front of experts. I have to recall what Berezinians are, for everybody to know what it is. So first of all, in supersetting, you have special kind of matrices. So you take a matrix and you have to introduce a labeling. The rows and columns are labeled with parity, with certain parity. Each row and column we have to label with a parity. And what's interesting, so it's not necessarily important, that this has nothing to do with the entries. So first you label them, and then putting entries is a separate matter. So a matrix is called even if when we start to populate it, that it has even entries in the even, and odd positions, and odd entries in even, odd, and odd, even positions. And matrix is called odd if it's vice versa. So also it's, people introduce standard format, and standard format is when you put all even rows up and all even columns on the left without shuffling within the same parity. So you just have to keep the same order. So what's Berezinian? Berezinian is a super, as I told you, it's the name of a super determinant. So you can define it the same way as the multiplicative functions on the matrices. But now it's on this matrices. It's going to be unique after taking powers. But it's also convenient to define it, by the properties. Okay, so here is, so first of all, the property is that Berezinian is homogeneous of degree +1 on each even row or even column. It's homogeneous of degree -1 in each odd row, so if you have multiplied by lambda, you factor out 1 over lambda, of course. And so Berezinian is invariant with respect to elementary row transformations, and here it's interesting that you can multiply by odd constants as well. And yeah, of course, Berezinian of identity is 1. So using this and Gaussian elimination, you can arrive to explicit formulas. So this is the 2 explicit formulas for Berezinians. And here, well, here's a standard format. Is when you, so here's all odd, you put them up, and so, yeah, so this is a standard format of your matrix. And so this is a block matrix, and this is how you compute the Berezinian. So one important thing to note straight away that this is a fraction. And actually, frequently people, so initially people say that, okay, maybe it's required that the whole matrix is invertible for Berezinian to be defined, but actually you can see that what you can use that actually only A11, the block of A11 is invertible. So again, another important thing in supersetting, which frequently very useful, is the parity inversion formula. Parity inversion formula. So what you take, it's sort of very simple, because you take a matrix and you change the format. So you change the format so the parities of rows and columns swap. And Bergelt and Radin they suggest to consider inverse Berezinian, which is just Berezinian of this, of this changed format matrix. So yes, if matrix A is invertible, so let's jump to case number 3. Then this Berezinians and inverse, they just reciprocal of each other. However, if what's interesting, so if only one block of this invertible, so it may happen that only Berezinian or Berezinian inverse exists. So not simultaneously, but they want to say Berezinian does not exist, but Berezinian inverse does exist. So that's become, of course, useful, and this is how it's usually used. So Berezinian is linear in even rows and columns, and Berezinian inverse is linear in odd rows and columns. So here is our little invention. So to get the compactor expansion, we met some difficulties. So what we had to do, we had to introduce the small idea of wrong matrix. So we say that wrong matrix is a matrix which is slightly off from an even matrix. So you take an even matrix and you notice one mistake. So say, for example, one even row or column is replaced by an odd vector. And in this case, you can still extend the definition of Berezinian by linearity. And or you made another mistake, or only one will allow. So one row or column is replaced by an even vector. And in this case, you can make sense of inverse Berezinian. So, well, the properties works. So the formula, you can compute the Berezinians of the wrong matrices by formulas, which you've seen before. The properties are slightly spoiled. For example, it's still invariant under the elementary transformations, but you have to be careful. So you're allowed to subtract only multiples of the correct say rows or correct columns. So to demonstrate, I'll give you a very trivial example. So if you want to compute this psi x, so the wrong part is this one, the first row. So because this has to be odd even, vice versa. So it's a wrong part. So what if we do a wrong step? Something not allowed, something was forbidden by this. So if we subtract the first row from the second, what you finish up, you have 0, 0 here. And so you cannot divide. So 0, 0 gets here, so you cannot divide. So we get into trouble. However, if you subtract the second row, which is correct row from the first row, you get 0, 0 here, and you're okay, you get 0. And this is how the Berezinian is computed by using the usual formula, so it's 0. Okay, so here's a compactor expansion theorem which we needed just for the Darboux transformation, so we had to derive it. So it turns out you could do expand this superdeterminant of Berezinians and have Berezinian with respect to along even row or even column, and Berezinian inverse along odd row and odd column. So he's like informal series informative book. So what actually it says the following. So when you do this expansion, but you consider even position, then the cofactor is just plus minus minor. But minor, of course, instead of determinant, you have to take superdeterminant of Berezinian. But the interesting thing happens when you consider in odd position, so you have to, this will be the formula for cofactor. Just one explanation, so what the notation means. So this is your matrix, and instead of Ri, we put Rj, and so the matrix becomes wrong. This is why we have to introduce it. So, and this djj, it's just, I don't know, introduce the operator when you cross out j row and j column. So this is one. Okay, I'm going to show a quick example because it's maybe looks convoluted what this is. So okay, so first, like this is Berezinian, so it's an even matrix. So we want to compute the Berezinian. So and we do it along the first column expansion. So the first element A11, so it's an even position. So it's the same like a classical case. It's just instead of determinant take Berezinians. So okay, so we cross the first row in the first column. So you're left with y. So A11 is x, so we'll put here x. And this Berezinian, well, observe that y is on the, it's in odd position. And therefore, the Berezinian of this matrix, which have y, is just 1 over y. So here we're applying. So here this element is standing on odd position. So it's beta. It's a beta here. So and here we have to apply this complicated formula. But it's So all that happens, you see that we substitute instead of the second row here, the first row x alpha. So cross cross. And again, alpha is here. Attention, depends. When you compute Berezinians of just one element, it's because we have labeling. It's important where it's like standing. So still, even if it's one element. So Berezinian inverse of this matrix where alpha is standing there has to be is alpha because it's inverse. Okay. Similarly here, so you just take original matrix cross cross. So you have y, so it has to be y. So Berezinian styles is y, so y squared should have to square. And here's just a common denominator, and we see that this is the same as the formula, which the standard formula for Berezinians. If you just don't know this expansion, this is how you would compute. So the same. So this is how it works. Okay, so we need to. Let's see. So let's now speak about. So we need now to introduce superjets. It's the same thing, very natural, except just want to attract your attention that we introduce it in terms of D capital. So again, D is odd operator. D is written there, so it's dxi plus xi dx. It's an odd operator, so it's going to change the parity. So, and because of D going to change the parity, naturally you have this, if like every bit, the dimension the parity is going to swap, and so that's why you have this dimensions of it pretty clearly. Okay, so this is, so why we need it? So, well, we need it for introduction of Supergronskin. So Supergronskin, it's almost as you expect, like the same thing but with D capital. The only thing you have to have, just to keep the format of the matrix, you have to either have this initial plug-in functions which you're planning to plug in into it, build this Vronskin. You should have either equal number of them or just even has to be +1, like more by 1. So and just to, instead of saying this at length, it's just another way of saying that let's require that we have plug-in functions with alternating parities. So that's why it's sort of provided by automatically. So and we say for clarification we say okay we start with given one. Okay, so double, so Vronsky, so and you already found that, okay, inverse parity, so Berezinian inverse is pretty important. So, you know, if we introduce super Vronsky, we also introduce inverse super Vronsky, which is Berezinian inverse of the same thing. So Vronsky and super Vronsky is linear in each even function, and Vronsky inverse is linear in each odd function. And also happens like a sort of typical properties. So here, how does it look like? So, I mean, so I just didn't show much, but okay, so this is to plug it in, and so you push. So when you put this in standard format, I guess it shows that, okay, final. So you see all the even guys are getting up here, and this is all this little odd community and odd community. So this is what happens. You have to rearrange. Okay, and then Berezinian inverse is the same thing. I just confused pretty. Okay, so now, so you see that I'm basically consistently reconstructing some results which actually I have been, people are using for Darboux transformations, but they were using it for ordinary case, and now I'm reconstructing in terms of this capital. So you can take your intuition from ordinary case. So what we proved, so the theorem is the following, the new theorem is the following. So every monic differential operator on the superline, so that looks like this, is defined by its kernel. And you can, build it in, so using the known kernel. So if but here this, you can see this. The formula looks very familiar, but there's something, the same thing you would do in ordinary differential equations, like class. But here there's of course some slight difficulties. So the actual, when you have odd, when the order of this operator is odd, you define M, this operator M, by the action on the arbitrary odd function. Because you see it's going to stand in an odd place. And then you have to extend this by linearity. And when the order of your operator is even, then you define how it acts on arbitrary even functions. It has to be signed. Yeah, on arbitrary, it defines its action on arbitrary even function, and so then extend M by linearity.
Because when you write a fraction, it means the denominator put on the left or on the right. Does it come to equal?
The number has to be even. So it will be, you could put it on the left and on the right.
Once you always even.
No, this one going to be even, because if you put something in denominator, you automatically even.
So the value of constant is always an even function.
Yes. I think on this is going to be, we just did that. Well, in the numerator it has to be. Let me think for a second. I'll just move on. Okay. So so again, that's another restoration of the classical result. So you could also, this is the same like in ordinary case, you can, given the kernel of your operator, you can write it down, like you can reconstruct the coefficients of these operators, right? So this is a formulas. You can apply, getting these formulas, you can apply Cramer's rule for the supersetting, which was developed in Berezinian work, or Darboux. So it's also formulas which you need for compressing and that sort of things, which is my general goal anyway was. So how many minutes I have?
5 minutes. 3 minutes.
Okay, excellent. I just wanted to get, because all of that I was wanted to do for this. So I just wanted to give you an idea, like a general idea what was that. So I'm going to consider Darboux transformations so we consider Darboux transformation in supersetting. And so we're going to consider only one intertwining operator, so there's only one, M, not M on M, because we kind of observed already that in non-degenerate, in the case of this non-degenerate operators on the superline, it's kind of like one-dimensional object. So, okay, so we consider this equality, and so L1, if it exists, so it's a few facts, is defined uniquely by L1, L0, and M. And not every operator M, of course, can give a Darboux transformation. And well, this is intertwining relation, so if it's actually it's operator equality, so it means it's actually give you an overdetermined system, and after you solve it all, M must satisfy some compatibility conditions. So this is we're going back to Darboux transformations, which I introduced in the very beginning. So just if anybody wondering what's going on right now. So, analogously to the classical case, for Darboux transformation, as I told you, the classical results in ordinary case. So, first of all, the order of Darboux transformation is the order of this, operator which is intertwined. So, the order of this operator M. So, I remind you what M phi is. So, we say that, okay, first of all, one result, every Darboux transformation of order 1 defined by M, this M phi, which looks like this, which is generated by phi, which is an eigenvalue of the original operator L0, which is, those who knows, it's exactly classical, analogous to classical result. Then, okay, if you have a large Darboux transformation of order R, then you can decompose it as a composition of elementary first order Darboux transformations. So in this case. So now, so one important thing in addition is the following. So this is just diagram from a previous slide. So you have one big Darboux transformation decomposed of many small. So the question is, what is something unique? What is the closed form for M? So if you want to classify, you want to describe it. So what's the closed form for this M? And so you don't want to. So how are you going to how you can write down the formula for it? So first of all, it turns out it's actually one theorem in this next slide as well. So first of all, what you can say that every Darboux transformation of order R between two non-degenerate differential operators is specified by actually some invariant subspace of original operator, but not any, but of this specific dimension. So these dimensions, and again you recognize, so you have either S plus 1 even and S odd, or like equal number. It has to be equal number, like dimension odd and even. And this is going to be actually corresponds to the kernel of this operator M. And specifically, here's it's like continuation of the theorem, but just for 2 slides. So, well, if you have a basis of this subspace for the previous one, this is specifically how you could define the operator M, which is, for Darboux transformation people, this is the kind of like how, this is how you can define it. So this is a formula, explicit formula for this. So if, for operator M. So yeah, so here I guess it's two things to observe and notice. So again, you have to use both inverse Berezinians and Berezinians, and I remind you that Berezinians are the fractions. So here you kind of have multi-story fractions. So this is a fraction, each of them is a fraction by itself, so you have a multi-story fractions. My couple of final slides on the dressing form. So so those people who work in Cycle series, so basic formulas are quite important. So basically for everyone else, dressing formulas is you tell how, so you have one operator and another operator, and you want to tell how your coefficients change, basically the dressing formula. You tell what is the formulas which change your coefficients. So for example, so here is an operator of fourth order, this, and I say that it's transformed to another operator L1, which have the same form, but I just denote the coefficients by B. I didn't have space to introduce it. But B is, L1 has the same form, but instead of A's are B's. So, okay, so let's consider the magic number transformation given by M of this form, D plus mu. Then this will be the, this will be dressing formula for this case, right? So just formulas for the D. Okay, so what did we prove in general? So this just was examples. So what did we prove in general? Well, it turns out, so this is what we could prove. So B1 and B2 is just the first two coefficients. It's just the first two coefficients. So we could prove in quite generality, but only for the first two coefficients, like after the leading one. So, but for random operator, for non-degenerate or the superline. So if you have odd one, then the B1 and B2, so it's the coefficients, is going to be expressed by this formula. And if the order is even of your operator, then this will be dressing for the first two coefficients after the leading. So here, well, one thing maybe which I could say straight away. Here, to me, it explains sort of it's giving an additional thing about idea about Supersturmlösung and why it was exactly considered like in this particular form. Well, I just write it down here. The Sturmlösung is what? It's d squared plus alpha d plus u, the one which I said. So okay, so this one is the same as d to the fourth. So you would say that well, obviously, what's missing is d cubed and this d cubed is missing, right? And d squared. So here we could see that if a1 is 0, then this condition. If a1 is 0, then this condition is preserved, and then also a2 this also condition is preserved. So this is why it maybe makes sense. But here is like I only have it for two first coefficients. Okay, and maybe now I just it's the end of my talk. I just want to show you maybe if people if you're interested just some references of which I mentioned. It's worth if you have interest in looking into this. And of course, you can work for details into our works, which are archived and published as well.
Okay, question. Okay, let's thank speaker one. Okay, so the next meeting begins at 1:30 p.m. No, let's see. 1:30. 1:30, yes.